In this example problem, we have a hot water tank with a certain volume that has a heater rated at 4,500 watts. And we want to know how much energy is required to heat the tank from 20 degrees Celsius to 60 degrees Celsius. And we want to know how long that would take. This used to be something people did when I was a kid. When you went on vacation, you would turn off your hot water tank while you were away. And nobody seems to do that anymore. I don't know whether it's because they're more energy efficient or they become safer. It's like nobody unplugs their television during an electric or a lightning storm anymore. Alright, so this problem's a little bit tricky because I'm asking first how much energy is required to heat it from one temperature to another, and that would indicate that you need to use the new equation we just learned to calculate the change in thermal energy or the heat. And you're given the two temperatures, so you can plug those in right away. And since it's a hot water tank, we can look up the specific heat of water in a table in the textbook. And I want to caution you guys once again about the units for this. Make sure you're in joules per kilogram degree Celsius. So make sure you note, whether it's the table linked in Blackboard or whether it's something you're using online, that the units match joules per kilogram degree Celsius. Joules per kilogram Kelvin is actually the exact same number, so you can use that as well. But make sure you're in kilograms, make sure you're in joules. But what's missing here is mass. And in order to find the mass, we actually have to go back to something we used in the prior unit, and that is the fact that density equals mass divided by volume. So we can look up in the table the density of water, and we have the volume so that we can find the mass to plug in. And I like to throw a couple of problems like these in where you're using prior material to remind you that the final exam is a cumulative final exam, so you can't forget stuff that you learned at the beginning of the semester. Now that we know what the mass is, you can calculate the heat or the change in thermal energy required. And we also have to use something from prior material in order to find the time. Power is equal to the change in energy per time. Earlier in the semester, we had the change in energy be work because we were dealing with mechanical energy. Now we're dealing with the change in thermal energy, which is heat. So we can say power equals heat divided by time. So I have the power provided in the problem. I have the heat that we calculated in part A, and I can solve for time. And please be careful when you're doing the calculations for this. It's really easy to accidentally find the inverse, so you need to multiply both sides by t and divide by the power in order to find the time. So be careful not to find the inverse by mistake. That gives us a time that conceptually we don't know how to conceptualize seconds very well unless they're very short increments like 30 or seconds or 60 seconds. So I can convert this to hours just so you can conceptualize how long that would actually be.